Hello, I'm Sihang. In this video, I'm going to talk about our work, cross-failure bug detection in persistent memory programs. This work is in collaboration among University of Virginia, University of Michigan, Penn State, and VMware Research. First, I'd like to briefly summarize this work. Programming for persistent memory is hard and error-prone. Previous works has been focusing on the correctness of the stage before failure by providing detecting tools. However, crash consistency relies on the stage both before and after the failure. In this work, we define cross-failure interactions between the two stages and provide XFDetector or cross-failure detector that holistically tests both stages across the failure. First, I'm going to introduce the benefits from using persistent memory. Persistent memory features high performance, byte addressability, and data persistence. Persistent memory provides better performance for two reasons. First, it is faster than conventional storage devices such as hard drive and SSD. Second, programs can bypass the operating system indirections, such as the file system, by directly accessing the persistent memory. However, the cost is programs to ensure the crash consistency of persistent data, such as the support provided by the file systems. In this way, the program can recover to a consistent state after failure. So, direct access to persistent memory benefits the performance, but it is hard for programming. Let's take a look at an example. On the persistent memory, there is an array, and we want to update the second item from B to E. The question is, how can we update B in a crash-consistent manner? One of the solutions is to follow the undo login mechanism. First, make a backup of the existing data, and second, perform the in-place update by changing B to E, and finally, commit the update. To guarantee crash consistency, the writes in each of the steps need to be persisted before the next step can start, and all the updates need to be persisted in the end. To support persistent memory programming, the hardware platform has introduced new primitives. This figure shows a memory hierarchy where the cache is volatile and the memory is persistent. The system first provides a durability guarantee, that is, a write can become durable on demand. In this example, after writing to location X, the program first issues a cache line write back instruction, or CLW, followed by a stall fence, or S fence, to make sure this write back is complete. And at this point, the location X has been persisted. To support the ordering guarantee, that is, one write can become persisted before another. After writing to X, it issues a CLW to X and an S fence to make sure X is persisted, then it can perform follow-up writes to location Y. And for simplicity, we refer to the combination of CLW plus an S fence as a persist barrier. Now let's go back to the example. The left side shows a code implementation of the crash consistency mechanism with 3 steps: backup, update, and commit. On the right side, there are 2 new data structures. One is the backup of the old data, and the other is valid, showing the validity of the backup. First, the program makes a backup of the array, and then it sets the value to 1 and uses the persist barrier to write back the backup and the valid. And then it does an in-place update and sets the value back to 0 and write back all the updates. It seems correct, but what if there's a failure? Because the writes can reorder, it's possible that the backup is not persisted before the valid. And then the program can use a non-persistent backup for the recovery, so it's causing inconsistencies. The solution is to insert more persistent barrier in between all the writes, and with the reordering disabled, the backup is always persisted before the valid, and it is crash consistent now. As we can see, programming for persistent memory is very hard. Programmers first need to come up with crash consistent mechanisms, and then correctly implementing the mechanism using the programming supports. As programming for persistent memory is hard, we need testing tools. Our previous work, PMTest, has provided testing for persistent memory by checking the 2 fundamental guarantees. First is the durability guarantee that writes become persistent in memory, and second is the ordering guarantee, that is, one write becomes persistent before another. In the previous example, programs can assert whether the backup has been persisted and whether the backup is persisted before the valid. But what happens after failure? In this work, We refer to the execution stage that performs normal execution, such as updating the persistent array, as the pre-failure stage. And after the failure, the program performs recovery followed by the resumption of the previously preempted normal execution in the post-failure stage. And we refer to the interactions across the pre- and post-failure stages as the cross-failure interactions. And any incorrect interactions across failure can lead to cross-consistency bugs. Therefore, a holistic testing across the failure is necessary to ensure cross-consistency. The goals of this work are: first, categorize the type of incorrect cross-failure interactions; second, precisely define such type of incorrect interactions; and finally, detect cross-consistency bugs based on the definitions. So far, I have introduced the background in persistent memory programming and the motivation for a cross-failure bug detection tool. Next, I'll talk about the categorization and definitions of different types of cross-failure bugs. In this work, we identify two categories of cross-failure bugs. The first type of bug is called cross-failure race, where the post-failure stage accesses data that is not guaranteed to be persisted before failure. And the second type is called cross-failure semantic bug, where the post-failure stage accesses data that are semantically inconsistent, according to the program. Recall the previous example where the backup is not written back explicitly. After failure, the post-failure program can read from such a non-persistent location. Let's make an analogy between persistence and concurrency. In a multi-threaded program, when a writer and a reader try to access the same piece of data concurrently, a data race occurs. For persistent memory, as data in such non-persistent location is determined, just like the data race scenario, the pre-failure actually acts as a writer and the post-failure actually acts as a reader. And we call this situation as a cross-failure race, that is, read from a potentially non-persistent location. More formally, a cross-failure race is defined as the post-failure execution reads from data modified by the pre-failure execution that is not guaranteed to be persisted before failure. As the value of such non-persistent data is unknown, the cache block can be evicted or not evicted or partially evicted, so what data remains on persistent memory is unclear. And the post-failure execution that depends on such unknown value is therefore undefined and can lead to undefined behavior later on. So the question arises, do all cross-failure races lead to bugs? Is there any exception? In this previous example, we have fixed the first bug, that is, making sure the backup is persisted before the failure can happen. But the recovery program can still read from the valid bit, which is not guaranteed to be persisted. So is the read from the valid a cross-failure race? Fortunately, PM hardware guarantees the cache line to persist atomically. Because the valid is only an integer or a boolean, it is guaranteed to be persisted atomically. So the valid can either be 0 or 1, and all the outcomes are well defined. If the value is 0, then the program can use the array as a consistent copy. If the value is 1, the program just rolls back with a backup. So the correct execution actually relies on such an intended race, and this behavior is correct. We refer to such a scenario a benign cross-failure race. More formally, a benign cross race is defined as the post-failure execution intentionally reads from potentially non-persistent data without causing inconsistencies. As the outcomes are all deterministic, the execution is correct. Let's again make an analogy with concurrency. Similar scenarios happens when the writer and the reader concurrently access synchronization primitives. Because all the outcomes are deterministic, it is correct. So far, I have talked about accessing non-persistent data in post-failure that leads to undefined behavior, and this situation is called a cross-failure race. How about accessing inconsistent data? Data consistency in persistent memory programs are defined by cross-consistency mechanisms, such as undo-redo logging, checkpointing, or shadow paging. These mechanisms typically keep two versions of data. One is consistent copy, the other is inconsistent. Such versioning is done by commit variables. The version commit variable is referring to is regarded as consistent, and the other version is inconsistent. In case the commit variable refers to an inconsistent version by mistake, a cross-failure semantic bug can happen. Let's take a look at the previous example again. The programmer makes a mistake where the variable is set to run in both places. During the pre-failure stage, the program updates the backup, sets the variable, performs the in-place update, and finally commits the updates. After failure, as the post-failure program depends on the valid, the incorrectly set variable can lead to the post-failure program access an inconsistent location because the backup is stale. So this violates the semantic of the program, and therefore we call such a situation as a cross-failure semantic bug, that is, reading from a semantically inconsistent location. More formally, a cross-failure semantic bug is a post-failure execution reads from data updated during the pre-failure that are semantically inconsistent. Different from the cross-failure race, which leads to non-deterministic behaviors, the cross-failure semantic bug is always incorrect. For more details about cross-failure semantic bug and more scenarios that fall into this bug, please refer to our paper. In summary, inconsistencies are due to incorrect interactions across failure. The pre-failure stage may not correctly implement a cross-consistency mechanism, and the post-failure stage may not properly restore the status. And the Venn diagram shows the two types of bugs. First is the cross-failure race. It is a bug unless it is benign. And the second type is a cross-failure semantic bug. In addition, one bug can be both a cross-failure semantic bug and a cross-failure race. For example, a semantically inconsistent location can also be non-persistent. And other types of bugs are out of scope because these can be detected by existing testing tools such as Valgrind and GDB. Next, I'll talk about our tool, XFDetector. XFDetector is a tool that detects bug interactions across the failure. XFDetector is a tool that detects incorrect interactions across failure for cross-consistency bugs. Unlike previous works that only detect one stage, that is, the stage before failure, XFDetector holistically detects both stages. As such cross-consistency bugs are due to failures, we need to introduce failure during the program execution and perform testing. In this code example, XFDetector injects failure before each of the ordering points, such as a persist barrier where data gets explicitly written back to persist memory. As the updates before the persist barrier can potentially be inconsistent, XFDetector injects a failure point to each of the places and perform testing before data becomes persistent. With failure injected to the program at runtime, XFDetector collects a trace of both the pre-failure and post-failure stages. To determine whether data persistence and consistencies are guaranteed, XFDetector maintains a shadow memory with a field persistence and consistency for each of the addresses. Then it replaces both traces by replaying the pre-failure trace to update the status, and then use the post-failure trace to check whether there's any access that's reading from a non-persisted or non-consistent location. Now let's put the mechanism of failure injection and bug detection together. First, the program needs to provide simple annotations of region of interest for detection, and then XFDetector injects failure before each of the ordering points. And at runtime, XFDetector collects a trace of both the pre-failure and post-failure for each of the failure points. And then, after the traces are collected, it does the detection by checking against there's any incorrect interactions. The first two stages are offline because they are executed before the program starts running, and the other two stages are at runtime. Finally, let's take a look at the performance of XFDetector. We evaluate XFDetector on our platform with Intel's DC persistent memory and use PinTool to get the pre- and post-failure traces. The test programs include micro-benchmarks and real-world workloads. Compared to the original lines of code, the annotation is very small amount. The first result shows the performance when the program handles one transaction. The y-axis shows execution time in seconds. XFDetector can complete the testing within 50 seconds, and each of the bars is broken into a pre-failure and post-failure stage. As the breakdown shows, most of the execution time is from the post-failure stage. This is because for each of the failure points, the program needs to run one post-failure stage. We also compare the performance with a pure PinTool that only tracks PM reads and writes. Despite the repeated post-failure execution, the slowdown over the pure PinTool is only 12x. So we can conclude that XFDetector is efficient at testing. The next evaluation scales up the number of transactions as the x-axis shows, and the primary y-axis shows the execution time in seconds, and the secondary axis shows the number of failure points we inject. As the number of transactions increase, the number of failure points also increase. At the same time, the execution time also increases linearly. The reason for the linear increase is because in our workloads, the post-failure execution only executes a fixed amount of steps. For example, only unroll the last uncommitted transaction rather than executing the entire transactions again. So we conclude that XFDetector is very scalable. Finally, we evaluate the detection capability of XFDetector. We first validated with synthetic bugs that we place in the micro benchmarks. And then during testing, we have found 4 new bugs, one in HashMap atomic program, one in Redis, and another in the LibPM OBJ library. Those bugs cannot be detected by previous works as they require holistic testing across the failure. In summary, a persistent memory program has 2 equally important execution stages, the pre-failure stage and the post-failure stage. In this work, we define 2 categories of bugs across the failure, a cross-failure race and a cross-failure semantic bug. We have provided XFDetector that holistically tests both stages, and found 4 new bugs in testing the programs. XFDetector is also open source as a link below. Thank you.